All right. So yeah, I've been doing a lot of the initial, very, very early on, basically the infrastructure behind working with the general index. So for a very, very brief overview for anyone unfamiliar, the general index is this massive public data set produced by a nonprofit led by Carl Mahmoud, where they index 107 million published manuscripts, and they extracted the keywords and something called n-grams from them, which are basically between 1 and 5 words that best represent the underlying topic. And they published this as just this massive data set of 35 billion rows of this natural language data set, basically mapping a lot of publications and like essentially human knowledge in the last 150 years or so. And having such a vast amount of data is really powerful. It's on the scale of something like some of these GPT-3 algorithms are trained on the order of billions to tens of billions of rows of documents. Although there are also some notable limitations in working with the general index, because we're not using the underlying manuscript and we actually don't have access to the underlying manuscript because of copyright constraints. So instead, we're working with these small subsets of keywords with that best represent actually what the manuscript is about, but don't actually tell us a lot about the semantics. So, in terms of modeling and actually being able to use this data, that's sort of a rather unique problem in that regard. It's like similar to using tweets or like Twitter threads for anyone working with like natural language data with those, but on an even smaller scale across a large range of publications. So it's a rather unique problem, and additionally, it's not really well documented. There's not a lot of work being done on the general index. It's kind of like a hidden treasure. I definitely had some struggle working with it, so I wanted to create sort of like a GitHub repository and just a little bit of an explanation of like how do you actually get started with this? Like what is the general index? What is the underlying data? And then get people thinking about like how do we actually use this? Um, so they provided us with a testing data set as a CSV, which is approximately 4,000 engrams across 750 manuscripts. And it represents a absolutely minuscule fraction of the overall data set. So it's difficult to make any explicit conclusions about the total data set, but it is very lightweight and easy for us to work with, especially in terms of visualizing the data. So the data is extracted from two topics, antediluvian, or the historical era before the biblical flood, as well as Hennig 86, which is a computer program written in 1988 by James S. Ferris for phylogenetic analysis. So they're rather niche topics, which comprise these 750 manuscripts in the underlying data set. So to get started, the first thing, of course, after defining all of our functions and imports, is to actually import the data set. So we're working with natural language data here. What that means is we're using words and strings, right? Which to our brains, it makes you a little bit appreciate just how powerful they are, because we can see these words and immediately pick out what are the most important parts, or even what is the topic of the manuscript. We can see like antediluvian flood, and we can say, oh, it's about the biblical flood or something like that. Whereas a machine doesn't understand words very well. Machines work quantitatively with numbers and bits. So how do we actually transform natural language data to a machine readable format? And the first step is to pre-process the data. So because computers work quantitatively, even like minor changes to words like antediluvian and antediluvians, for example, the computer will interpret as totally separate words because they're different. Even though they're off simply by a plural, we can quickly say that those are essentially the same words, but a computer will refer to them as totally different and might assign them to completely different topics, even though they should be the same. So what we can do is a technique called stemming and lemmatization, where we essentially get back to the root of the word and try and prevent this from happening. Additionally, there's what are called stop words, which are like the, and, for, etc., etc. And they can do the similar thing, but essentially the opposite. They can make a computer model think that all of these manuscripts or all of this data are the same or part of the same topic, where they all just have the word the, or the word and, or yada yada. So what we do is we can remove these stop words while also performing this stemming and lemmatization to get to the root of the word to get slightly more machine readable pre-processing techniques. But notably, and I noted it here, this is not always what you want to do. So something like Google Translate actually really needs these kind of semantics to accurately translate the word. So it's important to understand like what the actual use case of this, and maybe there's a future use case where we don't want to do this with the general index. But in the context of topic extraction and really just assigning a topic to these n-grams, doing this can help further the model's performance in grouping topics together in a more effective way. Additionally, so it uses a few Python libraries to actually pre-process the data. It uses Spacey, which is like this industrial strength natural language processing library. It does a really good job at tagging words, so it'll tell you whether a word is a noun or an adjective or a verb. It's been trained on billions upon billions of words across languages, and is really good at this technique. Whereas NLTK is this open source program that you basically give it a list of stop words, and it'll just remove them from the data set or the corpus that you're working with. And it also has its own pre-built stop word lists to use. So these are the two packages that I use for pre-processing the data. And then in terms of importing the data, what you end up with is these little n-grams. So what they are is literally a word that's a unigram right there, antediluvian, or a bigram, antediluvian refrain. So these are literally how the manuscripts are being represented in the data set. All of these are hashes that just allow you to quickly pull a unique manuscript from this large 35 billion row data set. But this is basically what we're working with. These lists of between 1 and 5 words for each n-gram, and manuscripts can have between 1 and many n-grams associated with them. So now we've pre-processed the data. Oops. Where am I? We've pre-processed the data, but how do we actually know we did anything? Like, how do we know what we did works, or how do we actually know what the underlying data is? We can look at a few rows of it, but even for something like 750 words, we can't go through every single row and evaluate what's going on. So we can refer to some data visualization techniques to see the broader population of words, as well as what are like the most popular words throughout the data set. Yes. Uh, I apologize. I can't see the graphs here. I don't know why they weren't included. I must have completely forgotten to include them. But can you see my screen still?
Yeah, we can see it.
Okay.
And I think one thing that's going to be really interesting here is as we continue to iterate on nodes, one of the features that is coming up, which I'm very excited for, is an iteration on the code platform that we have right now, which turns it from something that's more of a read only to something that's read, write, execute. So hopefully in the future, you may not even necessarily have to have the figure in your paper unless you immediately want it. Could be something where you just go to the code component that it's listed in and run the code itself to create the figure. So excited to see some of these changes coming up, especially now as we're scaling the dev team.
Absolutely. And I guess I definitely want to reiterate that being able to integrate the code right into a node, especially for something like this, which is very iterative, this is a very early on stage that I've been working on for the last couple of months, but being able to continue to produce this and have everyone pretty much run it on their own local machine for reproducibility, or to write to if they want to post some kind of like an update or a fix or something like that, it's really cool for this kind of project, and something I have not seen at all in my experience working with any sort of computer coding projects. But back to the visualization. So here we can look at pretty much a histogram of all the words and see how many times they are produced.
You're
What are the
not
most common?
sharing visualization on Discord, just a heads up.
Okay. Let me see if I. All right, is it there now?
Yeah, it's coming up. Yep.
Okay.
Thank you.
Okay, great. So now we can look at actually what the words are being represented for the manuscripts, and basically what are the most common ones that are being produced. So in both the unprocessed and pre-processed data, so the unprocessed data is up here, the pre-processed data is called tagged words for part of speech tagging. You can see that the most common word is antediluvian. And it shows up about 3,300 times. But more broadly, we can see how skewed this data is. So there's a couple words here that are being shown, between several hundred and several thousand times, whereas the vast majority are being shown between 1 and 10 times. So it's important to note that the data is going to be very skewed and that there's likely going to be a few words that might best represent the topic. And these are likely going to be more key, whereas these might be slightly more noisy words. But it's also difficult to understand exactly what these words are. So we can look at the top 20 words and see more explicitly what is the part of speech tagging actually doing. So in the unprocessed data, the most common word antediluvian, the second Hennig 86, and then we have a bunch of filler words, the, of, and yada yada. These don't really tell us a lot about what is actually the manuscript underlying. So even though the keywords were extracted to build the general index, um, they are still including these very filler words, which can cause algorithms or models to mistakenly think manuscripts are very similar in content, where they just both share the or of. Versus in the tagged words or the pre-processed words, the words have much more meaning behind them. So seventh, for example, could be referring to like the seventh king, patriarch, world, program, version, or referring to the Hennig 86 program, time. Like you just see words with far more meaning, and it's far more nouns and verbs and adverbs and adjectives that actually best represent the underlying topic. Right. So a couple other plots to note. This is just the term frequency. It's basically how frequent the extracted term is in the underlying topic. It's rather normal, very linear with a few peaks towards the end, the higher and lower ends. We can also see that from the pre-processing, um, the number of n-grams associated with each manuscript was roughly the same. So the pre-processing is not actually like removing n-grams. It's simply changing what the content underlying it within them. So that's a good thing to know. And then we can also look at the most frequent unigrams, bigrams, etc. And there's quite a few plots here, but they basically show the same thing that we saw above, which is that the tagging actually improves what the underlying content of these programs is and may help further models. If I go back to the PDF, can you see on Discord, are you still looking at the graphs?
Still looking at the graphs.
Okay, I will switch back.
We're going to get AV worked out, and for anyone who has suggestions, more than happy to hear them.
Right.
Alrighty.
So what we've done now is pre-process the data, but it's still in a natural language format, and it's still difficult to feed into a model. What we need to do is actually now process this data. And in order to do that, we need to convert it into a very machine readable format, essentially a matrix of numbers. But how do you turn words into numbers? You use something called embeddings. And what embeddings do is they basically use the semantics of the words on pre-trained models to just assign it to a vector. So instead of being a word for a word, or instead of being like a string to represent a word, it'll be a vector of numbers. And while this is not very machine readable to us, we can't look at some matrix of numbers and understand underlying subject matter or semantics. To machines, this is perfect. This is exactly what they want to see. They want to see numerical data that they can then do linear algebra on, pretty much to extract these topics. So this embedding technique is actually essential to how these models really work. And there's quite a few different ways to embed natural language data. There's quite a few different models that are trained to do this. There's some very interesting ones like BERT, which are like bidirectional transformers, which are more cutting edge. Or there are also ones that can just take a single word and embed it like a word to vector. But once we have this numerical matrix data of the natural language data, we can then start feeding it into models like clustering models that can then actually extract the data. And then once we cluster the data, we can look at the clusters and pull out the most frequent words as they appear back from the natural language data. And then we can start assigning these topics words to actually represent them in a more human and natural language state. So this is basically the data pipeline that it's following. So you input natural language data, you convert it to some sort of numerical data via this embedding. So it's a very key step in the processing for modeling. You want to reduce the dimensions to just make it slightly less complex and improve model performance. Cluster it into these topics. And then topic creation is where you pull out the underlying words that represent the clusters. And then you can reduce topics by how similar they are to one another and extract the keywords from there. And then finally, we can assign manuscripts their keywords. So this is basically the idea for the data pipeline. It was developed with a lot of influence based on something called Burr Topic by, I'm not going to be able to pronounce his name correctly, but he authored a white paper on it and wrote quite a few Medium articles that were very helpful to me in terms of how to actually go from natural language data to topics. He basically follows a very similar pipeline for his topic extraction modeling, so that was very useful. And then there's also a couple other Medium articles on comparing CPU versus GPU processing to further, improve the efficiency of this pipeline. So the first step is to embed the data. So this uses a GenSim embedding model. And all that really matters here is that it takes a script and it assigns it a vector. So rather than doing words or doing it for n-grams or something like that, it does it for manuscripts. So we can give each manuscript some numerical value that represents the underlying data. And then we can visualize how similar manuscripts are to one another using cosine similarity, which is just a similarity metric between manuscripts. But what this is basically a heat map showing which manuscripts are most similar to one another and which ones aren't. So what you look at here, it's a little bit noisy, but what you want to see pretty much is that some manuscripts, the white ones, and so these are likely a part of a similar topic versus black lines. These manuscripts are not as similar to most of the other manuscripts. And you're basically looking for some kind of structure here. And you can kind of see that, I think, at least within the lines, but I'm also not an expert in this. So then we reduce the dimensionality using this unifold manifold approximation reduction. And what this allows us to do is take some vector, this is like a 10-dimensional vector, and transform it into 2 dimensions so we can actually visualize what's going on a 2D graph. So here we can see the projection of this embedding, and we see a lot of data here. What I kind of see from doing this for a while is that there's a big cluster with a bunch of littler topics versus like a smaller cluster over here, which is slightly more removed. And this is like in my opinion, a good sign. So we know that the data is coming from 2 separate topics, antediluvian and Hennig 86. And we also know that antediluvian is far more popular than Hennig 86 based on the word counts that we saw from the data visualization. So we can see, we hope that this is the large antediluvian topic, and this might be the less prevalent Hennig 86. From here, we can then use a clustering algorithm to actually tell us, what are the clusters from here, which uses HDB scan, which is nice because it provides like a hierarchy of clusters. So we can use it to do not just topics, but also subtopics, and then combine them together based on how similar they are and give us a hierarchy of these topics when thinking ahead to the broader general index, which may be of who knows how many topics. So we can use this. This is basically what it does is it takes these points and it tries to assign them to a cluster and then color codes them. And there's a couple different flavors of it. And then from here, we can construct basically our first network of the data. So this is a minimum spanning tree, and it's basically the minimum distance to connect each of the nodes, roughly, based on how similar they are to one another. So again, it takes a very similar shape to the dimensional reduction, but it allows us to basically, you can traverse it from here, from any node, you can then find connect it to another node by following this minimum spanning tree. And this can be particularly useful if you're trying to, for example, like select peer reviewers, and you wanted to select. You have someone who publishes a manuscript, say here, and you want to assign them peer reviewers of very similar manuscripts. You could, then look at the authors of this cluster right here as they're the closest, and you could, reach out to them or solicit peer review, stuff like that. We can also then reduce the clustering. So this is a condensed linkage tree. It basically, like you can see, there's basically 3 clusters that are getting pulled out. It's another way of basically visualizing the clustering data. And then we can extract the keywords. So this is the part where we actually take these clusters and turn them back into human readable data in clusters. So we pull out from these clusters, these 3 different clusters, we pull out the most prevalent terms in each, which are shown here. And it's notable to say that in this current state on a small testing slice, it actually doesn't do a great job at pulling apart the different data. And I'll talk on that in a minute, but I don't think this is necessarily too bad of a thing. So it does a pretty good job at getting Hennig 86 in this one. So this is likely to be just the Hennig 86 programming thing, manuscripts, but they're also included in the antediluvian topic down here. So you can see that the most common word is antediluvian, but they also discuss Hennig 86 and version and software. So these are likely, it's not doing a perfect job at pulling apart the 2 distinct topics, but again, I don't really think that's necessarily a definitive thing, considering we're working on a testing slice of the data that is, 1/1 billionth the size.
So moving forward, we can begin to construct networks from these clustering algorithms. So, and we can do this in a couple different ways. So one of them shown above was this minimum spanning tree, which can help us traverse the graph in the most efficient way possible. But we can also, for example, look at the document embeddings and their similarity and try to connect them based on their cosine similarity for some threshold. And basically, if their similarity is above a threshold, they'll be connected, and if not, they won't be. And this can help initially pull apart some of the initial nodes and parameters, but there are also a number of different ways to assign these networks, which are definitely a future consideration. So here's another one using that cosine similarity. But from here, this is pretty much as far as I got in terms of developing this in advance of this community call. And I basically just wanted this to be a really good, hopefully an easy to understand starting point for anyone that wanted to get interested in working with the general index but didn't really understand how. This is basically like a framework for how you can actually import the data, do some processing on it, and begin to build these clusters to begin topic extraction and modeling. But more so than that, I think it's, for me, is a way to actually just begin to think of what this data set could be used for. If we're looking at the way that the data is represented and how it pulls apart these different topics, like how do we actually, what can we do with this? How can a topic extraction algorithm be used in the context of research publication or in decentralized science? Like something I've been very interested in looking for is how do you actually select peer reviewers for like an ARC? If an ARC wanted to solicit peer reviewers for one of their members' posts, how do you extract peer reviewers? How do you determine who is most qualified to actually review a particular article? Right now, that process is very much dominated by editors with their own. They'll have lists of potential peer reviewers, for example, and it's very much an opaque process, which is not really well understood why people get selected, and people are volunteering their time, and the whole process is very opaque and has time and time again been shown to be ineffective at actually validating the reproducibility or the integrity of these results. Versus an algorithm like this, for example, would be very very easily understood and transparent about the decision making that's going on. It could take an input manuscript, assign it not just keywords, but then to a topic, and then determine the most similar manuscripts and query authors in very similar fields and see, say someone has published, 3 articles in this very specific subtopic. For a manuscript in review, they might be a really great reviewer, and you could select them without even like previously having had contact with them. And this can be connected to the metadata of the general index to potentially, reach out to existing authors, or at the very least to determine, the similarity between articles. And then you combine this peer review selection with a protocol like Ants Review, for example, which basically developed a way to solicit peer review rewards from reviewers without revealing, the identity of the underlying reviewers or the manuscript. So in combination with like the peer review selection, you do this peer review solicitation, and now you have kind of like basically an end-to-end way of selecting peer reviewers and soliciting their involvement to actually review a manuscript. And suddenly you've like completely changed the way that peer review is done on like a publication standpoint, which is currently the way it is now is the way it has been for the last 100 years and is very entrenched in a lot of these very powerful institutions and these editors who have a lot of connections, and it's very much, kind of you have to be a part of the club. I think this a different way of doing it with a more like algorithmic focus and a more transparent process. I think offers a lot of benefit for the scientific community, and this is just one example of how I think this data set could be used. I mentioned that you could start doing automatic, keyword extraction. Assume this works, you can actually like assign keywords to a topic like Hennig 86 or program. If you have a manuscript in this topic, and they say the n-grams contain the words like Hennig 86 program and then version, and then you assign it those topics, and then you could zoom out with more similar software pieces and assign it to like the phylogenetic analysis subtopic of bioinformatics, and now you have a whole tree of topics that you can traverse down, especially in the context of, for example, like literature search, or lit review or anything like that, or in the context of querying papers that might be citable by a given paper, the idea of like open citation. I think there's a lot of potential for this data set in general, and I just think it's not really being talked about a lot because there's not really a lot of infrastructure there to work with, and it's a little bit difficult to understand like what is actually going on in the underneath, before we can actually begin to have those conversations about how it can be used for decentralized science. So that was a lot of rambling, but that was basically my inspiration behind doing this, is this hopefully get people's brains moving on what this data is to begin to brainstorm how it can actually be used in a more realistic sense and in a practical way as well.
Ian, this is incredible. As always, these are some of my favorite community calls. I love the idea of peer review selection through automation within the general index, and I love the potential that this has for helping to organize the underlying scientific record. So if you think about this in conjunction with the idea that we can assign fair metadata to information, which we just had the call on that, and I will hopefully be writing up a Twitter thread all around that, including ontologies as a portion of the metadata for a scientific paper where it's easily indexable so that anyone can come in and find papers that have worked on Hennig 86 and can actually reach out to anyone else who's done that. First off, for peer reviews. Second off, just for help. Because to your point, working with a lot of this information can be confusing. I could very much see this turning into a paper where one of the tags is general index. And then everyone knows, hey, Ian Hay is probably the guy to go talk to about this. There is so much potential behind that. I want to open up the floor to anyone else who has thoughts here. But if not, I would actually. So this is incredible, and I am excited to see this as a node. I can't wait until we get some of the platform features out and code itself can be integrated within this. A question for you, I guess, with regards to putting this on a DeSci node. Can you talk to us a little bit about the experience there and kind of what your thoughts were around it, how some of your research and your communication has changed through this platform, just anything that you would want to bring up around that?
Definitely. So I think that's part of the reason why I'm very interested in this project. Is it also seems like it could be a you integrating it within the nodes seems like a very perfect example of why the nodes are useful. I mean, right now it's it is very much in a PDF format, but you can integrate the code right into it. Which for something like this, which is pretty much entirely a coding project, previously just publishing a PDF and then including a GitHub link somewhere in the PDF is like not really a sustainable way to ensure code reproducibility, particularly as that's not really enforceable. But using this where I can basically write up a Jupyter notebook and then just have the cells be immediately runnable, I think is really great in terms of getting people reducing the barrier to entry for people to actually just rerun the code on their own local machine and see what's going on step by step, as well as more broadly just having more diligent reproducibility with a lot of these algorithms. And I think particularly for this, if this were something that would potentially be integrated in like an Arc or a Node, having the code directly integrated into it, I think is absolutely essential to its success. And in making sure that it is open and available for everyone, and that the changes that are being made or the just effectiveness of the underlying model is very quickly verifiable on your own local machine, rather than having to trust like a black box algorithm that you don't get to actually see or run the underlying code. And I think that's pretty groundbreaking as well, particularly for these, larger, more open source projects. I think it could be game changing for not just this model, but pretty much any model that could integrate with the Nodes platform.
Couldn't agree more. And one thing that I would actually love to see with respect to all of this is how your thoughts have grown over the course of this project. Because I think you've been working on this general index code for what, 4 months now, closing in maybe 3 to 4. Which the amount of progress that you've been able to make in 3 to 4 months is absolutely astounding. By the way, uh, but another feature that I think could actually have a lot of impact here is the history tab and the
Mm-hmm.
ability to see every 2 weeks whenever you publish this, okay, these are the changes that Ian has made thus far. Here are the points where maybe it wasn't necessarily the right assumption. You tested it out, it was wrong, and just continued moving. I think there's a lot
Yeah.
of power behind that.
I think there's a ton of power behind that. Especially there's a huge problem in science in general, but particularly in my opinion, in like the biosphere, in terms of publishing negative results or publishing things that don't work. There's just essentially no incentives to do that right now, particularly with just the way that this is structured. Especially because you publish things at the ends. You publish it once you have the positive results and you have the conclusion and you have, the great title with the clickbaity headline. But being able to actually see how these projects change over time allows you to include the things that didn't work without really having to worry about how it's going to impact the final project and how it's perceived. And I think from what I've seen in my line of work, like knowing what doesn't work is at times more important than knowing what does work. You don't want to try something that someone else has already tried and verified it doesn't work. But that happens literally all the time. Versus having a platform where you can iterate on it over time and include, how things update, especially in a project like this, where the goal is to, over time, scale it up to this 35 billion row data set. Obviously, that's not going to happen by just a flick of a switch going from 4,000 to 40 million or 40 billion. But being able to see how that progresses over time and the different considerations, when does like the optimization of the algorithms really start to matter? When does like hyperparameter optimization begin to be a huge bottleneck of model performance? and of just general updates to the algorithm. And how do you actually integrate, for example, like APIs into this? When does that begin to think? I think having that history and being able to see how it progresses is a absolutely incredible feature of the Nodes platform, and something that I think not just for coding, but I think a lot of scientific publication would benefit from.
I couldn't agree more. And I think even beyond that, it's seeing what didn't work, but also maybe someone else has knowledge around how to do one of these different algorithms, around how to shape one of them in a way where you may not have been able to figure it out in that moment. With the right guidance on a targeted question, you can actually take feedback and make the entire algorithm more efficient or improve everything that's been done here. So it's more transparency, both I guess from an ingress standpoint and from an egress standpoint. Give feedback coming in, and you can also give feedback to others who may want to try it.
Absolutely. I think that's a great point of being able to ask like super targeted questions, particularly like especially in something like this where you could integrate the code and then pull out, lines like 30 to 35. This is not working and I'm not entirely sure why. You're trying to do, X, Y, and Z. And then having someone be able to just directly reply to that, I think is a really, really cool feature.
And it kind of creates this larger tree of knowledge, especially whenever you start thinking about the concept of granular citations down to the level of an individual code file through DeSci, which is already up and published. And for anyone who's wondering, the website is dcite.org, DCITE. That gives a whole new level of communication and feedback. So I could not agree more. That's incredible. What has your experience with the Nodes platform been like, if you don't mind me asking?
Absolutely. I think it's really cool, especially considering that this is just an alpha state, and how things have integrated. What you can do right now is really, it seems like it makes me feel that like why haven't we been doing this for like a lot longer? Being able to add these like annotations in the PDF directly, I think are is absolutely essential, and is something that I don't understand why that hasn't been a thing for like a lot longer in the context of research publication, because it is like so useful even in terms of just reviewing literature. Being able to add annotations right there, right in the file, is really cool. I also think just integrating, I've said this before, but integrating the code component for reproducibility and just like being able to run the code, I think is also absolutely incredible. I really like that I can just like hit the code component and like begin running cells versus like if I pull up like the white paper of many of the algorithms I was like looking at for this, trying to then go to the GitHub and then like install the dependencies and whatnot, to actually be able to reproduce the code is like kind of a nightmare, especially when it's not well documented, which many of them are. And having that built right into the publication platform, and then having these like open science verification to ensure that like everything's up to date and it's compatible with certain things, or like what Python version, what libraries do you need. I think just lowers the barrier to entry, for actually like reproducing these results, which is like the first step to actually creating something new, is to reproduce what's already been done.
Could not agree more, and thank you. We got about 5 minutes left, so I want to open up the floor one more time to anyone who might have something to add. Does anyone have anything they want to ask? Any additional comments? Any clarification? Please feel free to come off mute and ask.
Hi, am I audible?
Hello?
Hello, am I audible?
Yeah, I can hear you.
Okay, great. Actually, I might be sounding foolish, but I just wanted to know, like, would I be able to add a small video component to this, in the part of the paper? Like, for example, right now we can't do that. We can only add pictures. But would it be something like clickable, and we can like add some kind of a short animation where the graph is changing, something like that?
Yes, you can. That's one of the components that we still have to add. So as I said, we're still early in development, but we're getting there quickly. One of the code components that we plan on enabling is videos linked directly in line. So you would be able to add a code component and then link it directly into an annotation in line with wherever it is that you want to show that information. So yes, and it should be pretty easy to do.
Thank you.
Absolutely. Does anyone else have questions, either around nodes or around all of Ian's incredible work on the general index?
More just a general question. Can you share this note? And then I can read through it.
Not yet. We haven't enabled sharing at this point because I think we want to do a little bit more robust feature set around collaboration. So it's not just anyone accessing the reason and making edits. But I think in the not too distant future, it's only share for collaboration. I'm going to go ahead and mute Torch. Sorry about that. So yeah, that is one that's definitely on the roadmap and coming down soon. It's possible that we have an MVP feature for collaboration, which is more view only, coming out sooner rather than later.
I guess in the time being until then, there is a GitHub repository I've been working in. So hopefully that could be a source just if you're looking to like read through or like copy it or run it on your own local machine, the old-fashioned way. That could be the way to do it for the time being, if you're interested. And I would be more than happy to talk about this more in the General Index channel, and to definitely discuss, what could be done better, what the next steps are pretty much for this project, because I think it's getting to a point where it's going to start scaling up. I pretty much hit the limits of this testing data set.
Sweet. Yeah.
And then when you hit the limits of the testing data set, you went out and bought a 30 terabyte hard drive to download the entire general index.
Yeah, I might have done that. My roommates are so mad at me because I keep throttling the internet downloading this thing.
It's
But
we need more copies of this data set in the world.
right, right. I couldn't agree more. And I'm very excited to start like actually scaling this up. And I think that's why I chose such a complicated modeling technique for something so small. Is that the reason is that looking ahead, I think it's going to scale really well with larger data sets, and I think really start to shine once there's a lot more topics and subtopics to pull out. So I'm like super excited to get started with that once I can figure out how to work with SQL databases.
I have complete and total faith that that's going to be coming in the near future, and it's going to be awesome. All right. Well, with that being said, I think that's pretty much it for the call. As always, thank you to everyone for joining. Thank you to Ian for all of this amazing work on the general index. We have a series of different calls that are coming up. So for starters, starting in 1 minute, we have Coffee House. So feel free to join. It's an informal setting where you can just hang out, get to know community members. For all of our alpha testers on the call, product support office hours happens tomorrow at 1 p.m. Eastern. Then the onboarding call for anyone who has additional questions happens at 9 a.m. Eastern on Wednesday. So feel free to come ask questions about science, Web3, Discord, DeSci, nodes, whatever it is you want to ask about. And then this Friday, we're going to be having Journal Club with Quinyoung Yu, who is doing a lot of work on fractional calculus using Julia language. So we're excited to see the node that he's put together for that. And we'll be recording and posting it online. As always, if you have questions, please put them in the Discord. We'll do our best to answer. Look for the bounty board coming up. And yeah, thank you, everyone.